Hey class, so I wanted to do another one going a little deeper into Gaussian geometry, Gaussian elimination. And I want to talk about the echelon and reduced row echelon form and the CR decomposition, and then show a little bit of using MATLAB to do some of this stuff. So to do all these things, I need a slightly bigger example than we've had so far, just to make some of the definitions make sense. So I'm going to be using this one. Let's see, how can I paste here? Oh, I guess I have to blow this up. Okay, there we go. So I'm going to use this system here. Whoops. Okay. And so writing this as a, in an augmented matrix form would be like this. So here I would have, whoops. Let's see what's that doing here. Don't want to do that. I lose some of my controls when I have the screen split. Okay. So let's try that again. Okay, so here I have 1, 2, 1, minus 1, 2, 4, 2, minus 2, minus 1, 0, 1, 3, 2, 2, 0, minus 4, 1, 0, minus 1, minus 3, and then the augmented column here is minus 3, minus 4, minus 1, and 5. Okay, so that's the matrix form of the thing. And we want to apply these same row operations to this matrix to try to solve it, and we'll see what that means in this case. Now here we're not going to get an upper triangular matrix, but we're going to get an echelon matrix. So let me say exactly what that is. So in an echelon matrix, what you have is you have non-zero things, say, in the first place in a row, right? I'm going to use a star for something that's not 0. Okay, and then you have, after that, you just have some entries, and who knows what they are. And then here I might have 0 and 0 and then another star, like that. And then some entries, right, whatever they are. So we're really just interested in sort of where these first non-zero things in each row are. Below one of these things, these will all be zeros, right? And below this will all be zeros, right? So this is the way a echelon matrix looks. So basically what it says is when you go across a row, any row, and you hit the first thing, which is non-zero, everything below that has to be 0, right? And so what you get when you have a echelon form matrix is you get this kind of diagonal-like thing, but it's not really diagonal. It's really this kind of stair-stepped matrix, but it's kind of the best you can do in non-square matrices in terms of getting things like diagonal. I'm sorry, I keep saying diagonal, I mean upper triangular. Okay, so that's going to be the goal here. Not only am I going to do this by hand here, but I'm also going to do it using MATLAB, and I think I'll try to do this at the same time so we can see these kind of side by side as I do them. And I'm going to do it without using any fancy MATLAB stuff. I'm just going to do it brute force, sort of. I can make this a little bit bigger that way. Okay. All right, and so like, what will I do? So here, right, what I want to do is I want to, kill off all of those, right? So I'm going to use, R2 minus 2R1, right, and replace R2. And I'm going to take R3 minus R1 and replace R3. And then I'm going to take R4 plus R1 and replace R4. Okay, and I'm going to do the do the same thing over here in MATLAB, and partially to check what I'm doing here is correct, and partially just to show you how to do it in MATLAB. And by the way, when I want to enter this matrix in the MATLAB, sorry, all you do when entering a matrix is you just enter the row entries, and you can just hit an enter and then go down to the next row like this. Enter the row entries, the row entries, or if or if you want to separate these, you can put a semicolon there, right? So it's pretty easy to enter matrices here. Also, for this particular case, I know an answer here. I know that one answer is so one x1, x1, x2, x3, x4, x5 will be 1 minus 1, 1 minus 1, 1 because I built it that way. So this b here, this part over here, the part that we're saying these things are equal to, is being given by that, right? So that's this part right here. Let's see, we don't need the reduced row echelon form now. Just to make it clear, to make the augmented matrix, maybe I'll call that one B, I can just write equal to A, which is my matrix, and then I want to add in another column, so I can just put a space and put B there, right? And then when I hit that, then I get my matrix, augmented matrix here, right, with the extra column there. Everything's really squished up here, so it's kind of hard to see. We can pull that just a little bit further. It's still pretty squished up. Okay. Now over here on this side, so let's just do this by hand first. So let's see what we get. So here I'm going to get 1, 0, 0, 0. I sort of created things to do that. And now what I'm doing here is I'm subtracting 2 of these from that, right? So again, this will be, so nothing in the first row changes. So it'll be 2 minus 1, 2, 1, minus 3. Nothing will change there. Here I'm subtracting 2 of the first things, so this will also be 0. This one will become 2. This one will become minus 2. This one will become minus 2. This one will become minus 4 plus 6, so it'll become 2. And then here I'm subtracting 1, so this one will also become 0. Here I'm subtracting 1, so this will become 2. Here, let's see if I can get myself confused here. Here I am subtracting this, so I get minus 2. Here I get minus 1, so another minus 2. And here I get a minus 1. I'm subtracting this, so it'll become 2, right? So now those two are exactly the same. And then let me just make a little bit more space down here. So then I have my 0 here. And now here I'm adding 1, right? So again, I get 0 here. I add 1 and I get 2 here. And I add this and I get minus 2 here. And I add this and get minus 2 here. And I add this and get 2 here. So you can see that's interesting, right? All those are the same, right? So clearly in the next step of this, right, I'm going to replace row 3 and row 4 by just subtracting off a row 2, right? So I'm going to have row 3 minus row 2, replace row 3, and I'm going to have row 4 minus row 2, replace row 4. By the way, this is not echelon yet, right? So I come across here first. So this is a pivot, right? So the first non-zero thing I hit here is that 1, and then I've made everything below there. That's good. This is not a pivot because it's not the first non-zero thing in a row. Now I go across here. This is a pivot, right? Now this is not echelon form because the things below that pivot are not 0, right? So I need to do this step. And then I get 1, 0, 0, 0, and I get 2, 0, 0, 0, and minus 1, 2. Now these will just become 0 because that's what I'm doing. And of course, the same thing is going to happen here too. So it'll be 2 minus 2, 0, 0, and then let's see how many. Here, here, here. This will become 1 minus 2, 0, 0. This will become 3, 2, 0, 0. Right? Yep, that's right. Okay, so that's what we get. By the way, this is the augmented part of the column over there. Good. Okay, so now this is an echelon form. First thing I go across a row, hit a non-zero thing, everything below is 0. Next thing, pivot. Next row, first non-zero, I hit that, everything below there is 0. And then here, when you get to these rows, everything's just 0. And that's what has to happen in an echelon form, is at the very bottom, if the rows might all be 0, so that might happen like that, right? So this is definitely nothing like a upper triangular matrix, right? It's not even square, so that doesn't make sense. But it does have this nice kind of stair-stepped form, right? So it's like that. And we do the same thing here. We do a back substitution, but here now it gets a little bit more interesting because these two variables. So right here, this is x1 and x2. These are the pivot variables. Sorry, this is x3. These are pivot variables. Or we call them bound variables, okay? And then these guys are the non-pivot variables, x2, x4, and x5. These are the free variables. Now this turns out to be a really important notion, and also keeping in mind the relation to the corresponding set of equations that these things correspond to. Which we will write down here in just a second. So so what equations does this correspond to? We do want to do like back substitution here, right? And so here I have 2x3 minus 2x4 minus 2x5 equals 2, right? I have that. There's no way to solve for x4 and x5 because there's not anything to solve for here. So here we just have to say, these are why these are called free variables. We say let say x4 equal, I don't know, s, and x5 equal t, right? And then what happens here is I have 2x3 equals 2 plus 2s plus 2t, like that. Okay, so we have this. So now we haven't quite solved for x3, right? So x3 is actually equal to, now we divide by 2, right? So it's just 1 plus s plus t, right? So we have that. And then we look at our first equation. It says x1 plus 2x2, and then we have minus x3 plus 2x4 plus x5 equals 3, right? But now we already have that x4 is s, so let's just put in what we know. So x1, now again, we can't solve for x2 because there's nothing to solve for there, so we're going to just have to say it's the other free variable here. So x2, let's call it r, right? So this is going to be plus 2r minus, and then what was x3? Well, x3 was this thing, right? So 1 plus s plus t, right? And then plus, and then x4 was s, so this is 2s, and x5 was t, equals 3, right? And then we're going to clean all this up and get x1 plus 2r, and then I have here minus 1, and then I have, let's see, we have a minus s and plus a 2s, so it's going to become plus s, and then I have a minus t and plus a t, so that's just going to go away, and then I have 3, like that. So I have x1 equals, bring that stuff over here, so minus 2r minus s, that's going to become plus 4, right, like that. Good, and then the solution I actually get here is like this, right? So the solutions are going to be those x1, x2, x3, x4, x5 that look like this. So the free variables here, so x2 was just r, right? X4 was just s, x5 was t, okay? And then x1 was this thing, so minus 2r minus s plus 4. And x3 was this thing, so 1 plus s plus t, like that. Okay. And so we get here, so let's call this x bar. This is my solution. It's a 5 tuple, right? And so we get x bar, and I'm going to write this out as vectors added together. So this looks nice like this. This is 4. It's a 4, and there's a 1 there. So 4, 0, 1, 0, 0. Plus, and then I'm going to have r, and then I'm going to have minus 2, 1, and there's no r's down there. So 0, 0, 0. And then plus, I'm going to have an s, and I'm going to have a minus 1, 0, 1, 1, 0. And I'm going to have a plus and a t. Okay, and for the t's, I'm going to have no t's there, so 0, 0, 1, 0, 1. 0, 0, 1, 0, 1. Good. Okay. And the important thing is that, what is this? Well, this is all of these things summed together with just these free variables substituted with, any real number. So all the linear combinations of these vectors right here, this is a subspace, okay? And this turns out to be the subspace we're going to call NS of the null space of the original matrix A. And the original matrix is way back here, this part, the coefficient matrix there, right? So it's going to be the null space of A, okay? And this part right here will be a particular solution of our equation. So the set of all solutions will be this particular solution plus any of these infinitely many, combinations of those three vectors there. It's a three-dimensional subspace of R5 is what it is, right? And so this is interesting, right? This is a different solution than the one that I started with. Remember, I made up this problem, so I know that 1 minus 1, 1 minus 1, 1 is a solution, right? So I know that I can take 1 minus 1, 1 minus 1, 1 and write it in this form. Okay, that's part of what we're showing here. And it's interesting that the thing that I got here through this method is not the same as this 1 minus 1, etc. But that's not surprising because there's a whole lot of solutions to this thing. So, 1 minus 1, 1 minus 1, 1. This one is just one of those solutions. This is another one of those solutions. And I'll use MATLAB in just a minute to show you how to easily find other solutions too. One of the things you want to do is you want to be able to find this particular way of writing the null space, okay? So let me just focus on that just a little bit more. Way up here at the top, let's just take this. Let me copy part of this stuff here. So I get a copy down here. Let's just take that part right there. And let's, I want to do copy, so copy it. Okay, I want to bring it down here and I want to paste it. Can I just Control V? There we go. So there's a copy there. Okay, and then what I want to do is I want to kind of change what I've written here. So this is the original system. There's the coefficient matrix right here. There's the extra B part right there. So let me cut that part off too. Okay. Whoops, I grabbed more than I wanted to. Bring that over there. Okay. Oops. Okay, so let me put the 3 back here. Get rid of that there. Okay. And then draw, and then I can say here, we're multiplying by x1, x2, x3, x4, x5, right? And the result is going to be that thing there, right? So this has the form A. This is a 4 by 5 matrix times x bar. This is a 5 by 1 matrix. We're multiplying these things together. And so the result is a 4 by 1. This is that thing, 4 by 1, right, in R4. So this is equal to B, right? So this is the thing I'm calling B over here. So we have this kind of equation. When you're solving for the null space of A is the set of all x, where in R5 from here, such that ax equals 0, not b, but 0. Right? So it's called the null space, or it may be called the kernel of A. Okay. And we're going to see these again when we get to eigenspaces, because that's part of what you do when you compute eigenvectors. The eigenspaces are actually the null spaces of certain matrices. But using this method to compute the null spaces is really important. So why does this method compute the null space here? Well, if I were to, instead of augmenting this, with this thing here, I just augmented it with 0, right? Then I would have this coefficient matrix in zeros. But as I went through the process, nothing would happen to those zeros. They would just stay 0. So you just leave them off, right? And then you do exactly the same process. You do exactly the same process we had here. You just forget about this extra augmented column over here. And you do exactly the same thing that we did down here, except instead of having these numbers like 2 here and 3 here, we just have 0 and 0 there, right? And so you do all the same stuff, and the only thing that changes would be that this part here would just not be there. We would have just this part. That would be the null space part. So we'll do one of those when we get to the eigenvector stuff too. Let's see, I have 8 minutes here. Good. Okay, so let me just do a little bit of this stuff in MATLAB too, just to show you how it's done. So like this was my original matrix. Here's my original matrix. Let me just blow this up. Let's see. So see, this is my augmented matrix, right? So I'll just give myself an extra break here. I'll just do this sort of one step at a time. So what I wanted to do, right, was I wanted to take, to replace this row with this row minus 2 of those rows, and replace this row with this row minus that row, and place this row with this row plus that row. So we do that like this. I'm going to say, yeah, we do it like this, right? So I'm going to say B, so this is this augmented matrix. Let's see, it's been a while since I've done this. 2, because I'm looking at that row, and I'm looking at everything in that row. And what's it going to be? It's going to be equal to, now this is actually going to change what it is. So it's going to be B to that. So this is going to be the old version of the row. This will be the new version of that row, okay? And I'm going to say subtract off 2 times B1, right? So the first row, right? So that's what I want. And then the next operation I want here will be, and then to keep this from showing up each time, I can put a semicolon there. So the next operation is going to be sort of the same. So let me just copy this so I can use it as a template, except I'm going to be dealing with a third row. So it's 3, 3, and I just want to subtract off 1 instead of 2. And then the last one will be, again, more or less the same, except it's going to be 4, 4. And then here I'm going to be adding 1, or subtracting off a minus 1. I could do it like that, right? So I could do it like that. And then at the end, I just want to look at the B we get. So there, I'll do that. So I'll just have it type out B for me. Then I'll run that. And it does all that stuff. And there's what I get, right? If you think about it, that's exactly what I had in my notes here, right? That's exactly this matrix here after we did those operations, right? So that's good, right? And then we can just do the same thing again. So let's get another section break in. Oops, I did not mean to do that. Okay, let's just rerun this. Run that, run that. Okay, what I meant to do was section break. Okay, so I want to do the next bit, and the next bit is to just kill off these rows using that one, right? So I have, actually I'll well, now here, I'll just type it again. So it'll be B3 stuff, and then minus, sorry, equals. So the new one's gonna be equal to the old one minus row 2. By the way, there are cleaner ways of doing what I'm doing here too. I'm just doing the very most brute force way. Same thing. And let's get B, right? And we do that. And so we get that. So good. So that's same matrix we got, right? Okay, so that's good. And by the way, there is ways of getting MATLAB. I could just type in null, null A, right? And it would actually give me the basis for the null space. So like there's lots of things MATLAB can do here for you. Let me just see. Okay, I wanted to do just a little bit more here. So I erased all this stuff that I had here, and here was our original system. Here is the coefficient matrix A. That's the matrix formed by this stuff in here. And then here's the B, which is this part over here, right? So we're solving the system AX equals B. And the way we did it is we made an augmented matrix where we took A and put it in part of it and put B, as another column to the right. And what we got out when we were all done was this matrix here. This part is an echelon form. Okay, and then this, of course, is just the augmented part. Okay, and we got a solution. I actually made a small error in the solution, so we'll see that in just a minute. I want to say here that we could go on, right? So we could go on, and instead of writing out the equations and using back substitution, everywhere where we have a pivot column, we could just get rid of everything except the pivot element. So there's the pivot there, and it's the only non-zero element in that column. But here's the next pivot, and there's two things that could be improved with this one. We could make that into a 1. And we could get rid of the thing up there so that we had just that 1, 1 in that column there. So let's do that. So let's take this, let's keep going in our reduction. So let's take this thing here and let's first do, replace row 2 with 1/2 row 2, 2, okay? And then we will get a new matrix. I'm gonna see if I can save myself a little time by just like copying this, copy, and then let's see, can I paste? Yeah, I can. Okay, let's do that. Just copy and paste and do that. And then I will just sort of clean up what I don't want here. And then what I need to do is I need to change this, all of those. Good. Okay, so this will become 1. This will be -1. This will be -1. And this will be 1, right? So after doing that. And then I'm going to do it again. So let me do the same sort of thing. So I will copy this again. Okay, copy, and I'm going to paste it again right here. Maybe give myself there, and then and so once I get to this, I want to get rid of that guy there. So what am I going to do? I'm going to do row 1 plus row 2, replace row 1. And so what's going to change? These entries right here and this entry right here. And so when I add that up, I get 0, which is the whole point. So that's 0. When I add that up, I get 1. When I add that up, I get 0 again. When I add that up, I get -2. Right? And again, here's my pivot. Right? And so again, just to emphasize this is our free variables. So this I'm going to call that free variable. I'm going to make it R. That one I'm going to make it S. This one I'm going to make it T. Okay. And so we can just sort of look at this now and just immediately read off what's going on here. So, all right, x1, x2, x3, x4, x5, right, is going to be, these are going to be the solutions, right? And x2 we know is R, and x4 and x5 we know are S and T, so those are given. And then here, right, we're going to have 1, and then we're going to move those over to the other side of the equality. So we're going to have plus S plus T. So we're going to have 1 plus S plus T. And up here, we're going to have -2. And this is where I had the mistake. Earlier, I had 4, so I had made a mistake there. And I will move those over, and so then I'm going to have minus 2r minus s right there. Okay. And again, it's useful to write this out as a vector form, right? So this is minus 2, 0, 1, 0, 0. And we could have caught my mistake earlier because I said earlier that this thing here should be a specific solution, right? So in particular, ax naught should equal to b. Maybe let's just check that in MATLAB just to verify that once. And then I have the rest of this stuff here, right? So this would be r times, and I have minus 2. I think I had all this part right. And then 1, 0, 0, 0 plus s. And then this is going to be minus 1, 0, 1, 1, 0, and then t. And, oops, right, I need a plus. Yeah, okay, plus t. And then times 0, 0, 1, that's a t. 0, 0, 1, 0, 1, right? That's what that one's going to be. Okay. And as you recall, I said this was the null space of A, the same A I had up there, and that this, just to make sure we understand what this is the set of all x, such that ax equals 0. Okay. And by the way, an equation like this, where you have 0 on that side, is called homogeneous. So what you get here is you get that the solution, right, so let me just write it out as a sentence. All solutions, oops, let's wait for a second. All solutions of ax equals b are of the form x naught plus, let's say, z, where x naught is a particular solution. In other words, ax naught does equal b, and z is a solution to the homogeneous equation. We'll see this when we look at differential equations too. The same kind of thing happens. You often get solutions to things, or you get one specific solution plus a space of other solutions, which are solutions to homogeneous things, right? So that kind of thing is happening here too. Okay, so right now I'm just sort of rephrasing some of the stuff I said earlier, but what I really want to kind of focus on is this matrix that we got right here is a special kind of echelon form, namely in these pivot columns, there's exactly 1, 1, and everything else is 0, right? So the echelon forms that are of that form are called reduced row echelon form. So I'll just say that. Okay, so one thing I want to do is just notice this. So here I did the same calculation in MATLAB, right? And so just as we were doing before, I said, you know, here was the echelon matrix we got before. Here I'm dividing this row by half, right? So I'm just saying take the second row and replace it with half of the second row. And then once I do that, I get this matrix, and I'm wanting to get rid of that 1 there. So I'm going to add this row to that row and replace that row, right? So that's what this does, and I get this matrix here. Sorry, I get this matrix here, right, which was what we had in these notes a minute ago. So there's how you do it in MATLAB. Now, the nice thing about reduced row echelon form is it's unique. And so, in fact, there's just a function that does that, RREFA, and just gives you this reduced row echelon form like that. It doesn't give you the augmented column over here, so you can't use it to find the specific solution, But once you have this, you can use this to easily find the null space, right? So the set of solutions to the homogeneous system. So if you could some way find one specific solution, you can use this sort of easy step to find this null space here and get that. And one other thing about this is it gives us nice kind of what's called a decomposition of the matrix A that I want to look at real quick. And so I just want to sort of concentrate on again what the null space means. So I want to look at this specific thing we got up here. Let me just make a copy of that for myself. Whoops, that's what I wanted to do. That's over here. Okay, undo that. I wanted to do this. Grab that and make a copy. Okay, put this down here. Okay, so there's a copy of that. Yeah. So I mean this is the set of vectors like that, right? So if I put it like a set notation around here, right? Where R, S, and T are in R, right? This is the null space of A, right? These are exactly the set of all X, set of all X, such that AX equals 0. Okay. So I want to look at this. I want to look at this, and I do want to keep in mind what this reduced rational matrix is. So I have a copy of it over here, so I'll just sort of keep that there to look at. If I write A out in columns, so it's got 5 columns, I'm just going to write it like this: A2, A3, A4, A5. All right, then saying that A times this thing over here is 0, so then I have times this thing. So, oh, sorry, it's not. I need to get rid of the integer part here. Right, the null space is just that part there. So then I have minus 2r minus s, and I have r, s plus t, I have s and t. All right, and this is going to give me 0, 0, 0, 0, right, like that. Okay, so all this means, remember this sort of 2 different interpretations of systems of equations. Remember, this is just the columns of A. So I'll write out exactly what I get in the end here, but I just want to sort of work through this without having to write out all those numbers. So this is minus 2r minus t plus a2 times r plus a3 times s plus t plus a4 times s plus a5 times t equals the 0 vector, always, right? So that's what we get. And what I'm going to do is I'm going to take r equal 1 and s equals 0 and t equals 0 and sort of see what happens, and then take r equals 0 and s equals 1 and t equals 0. Remember, we can do this because, r, s, and t are just arbitrary real numbers. And then r equals 0, s equals 0, and t equals 1. All right, so I'm going to make one of them 1 while the other 2 are 0 and see what I get. So in this first case, right, what I get here is minus 2 a1 plus a2 equals 0. All right, so that's going to tell me that a2 is equal to 2a1. Okay. And then what I get here is I get that minus a1 plus, this was, s is 1, right? So plus a3 plus a4 is equal to 0. And so what I get here is I get what do I get here? Oh, yeah. I get a4. The way I'm trying to think about the way I want to write this. I get a4 is equal to a1 minus 2a3. Let me make sure I didn't make a mistake there. I get 1A1. Yeah, I think that's right? And then when I put t equal to 1, right? Oh, you know what? Sorry about this. This is not right. This was s equal to 1. There's no s there, right? The s's are all over here. So sorry, this is a3s plus a4s. That's all this is, equals 0. Right, and so this is going to give me a4 equals, and I should not be writing the s is just 1, so a4 is equal to minus a3. That's what I say. And then finally this last one, so I have minus a1 plus a3 plus a5, oops, equals 0, and so I get a5 equals a1 minus a3, right? So like that. Okay, so I'm getting those guys there. Okay, and then what I want to do is I want to look and see what it's sort of saying over here. So if I look at my reduced echelon form over here, right, I can kind of see these things here, right? So this right here, this 2 says that this A2 is going to be 2A1, right? I mean, I'm telling you that's what it says. I'm going to sort of write this out in the matrix form in a minute, but that's what this is saying here. And then over here, I go to this column here, and it's saying here that A4 is equal to A1 minus A3. So here I have let me see. Somehow I'm getting something a little screwy here. I see what I did. Oh, bad me. Okay, sorry for making this mistake. I have to go back and fix this. And I have to, okay, sorry about this, everybody. This happens. Okay, I had it right the first time. So let's go back to here, right? So I have s equals 1, r and t equals 0. So like I had originally said, this turns into s is 1, so this turns minus a1. This is a3, t is 0, right? And then a4. All right, and so this turns into a4 equals a1 minus a3, which is what I had originally written and should have left. Okay, and then this, when I put t equal to 1, then this is a3 plus a5 equals 0, and so I get a5 equals minus a3. Okay, so if you look at the reduced row echelon form matrix here, right? So this one here, actually, let me just take a quick copy of this and post it in here. Copy. Whoa, so big. It's small. Okay, so this is the reduced row echelon form, and if I think of this as sort of telling me something about, I'm not sure exactly how to say this in a way that completely makes sense. I mean, you kind of just have to think about it some, but A1 and A3 are the two pivot columns, right? So I'm sort of saying this is I don't know, maybe like X1 and X3, right? These are the two sort of corresponding pivot things. These are X2. I'm sure I don't really want to say X2, but let me just go ahead. This is X4 and X5, kind of, right? And so the point is, you can see that this says this is where I'm getting the A2 is equal to 2A1, because there's a 2 and it's just about the A1. And this is saying A4 is equal to A1 minus A3, right? I don't know, maybe I should just say these are somehow related to the A's instead of the X's. All right, and then A5 is minus A3, right? So you're sort of seeing that here, right? I mean, in some sense, we're just, I mean, I'm not doing anything deep. I'm just using this fact and kind of interpreting it in this way. But the point is, I'm saying I can read this stuff off of this matrix. And so in particular, using matrix multiplication, if I put A1 and A3 here as two columns of a matrix, right? So now what is this? This is a 4 by 2 matrix, right? Remember our original A is 4 by 5, right? It's a 4 by 2 matrix. And then here, I'm going to have a 2 by 5 matrix, namely this one. Right. So these are just the non-zero rows of the reduced to echelon form. These are just the two columns of A that correspond to the pivot columns, right? A1 and A3. So the two pivot columns. All right, and what these relations tell me is that when I multiply this matrix out, I get exactly A back. I mean, so this is a 2 by 5 matrix, right? So when I multiply these things, it's going to be a 4 by 5 matrix. And what I get out in the end is exactly, I mean, let's just think about what you get out in the end, right? I guess in some sense I'm jumping the gun. The bad thing here is I haven't done the discussion of matrix algebra, but on the other hand, I might not do that because we can't do everything in a whole linear algebra class in these videos. I'm kind of jumping ahead a little bit, but how does this matrix multiplication work? So what I get for the first column here is I get the linear combination of these two things given by this first column here. So I get A1 plus 0 A3, so I just get A1, right? And then what I get here for the next column is I get 2A1. And then what I get here for the next column is I get A3. And then what I get for the next column is A1 minus A3. And then what I get for the last column is minus A3. Right, so that's what this multiplication gives me, but notice from what we had above that this is just exactly A1, A2, A3, A4, A5, which is just A, right? Okay, so what I'm getting here is I'm getting that A is equal to these two pivot columns taken from A, and then together with the non-zero rows of the reduced echelon form. Right, like that. So this we call C, the pivot columns of A. And again, where are these pivot columns coming from? We find any echelon form actually, figure out where the pivots are, and go back and grab those pivot columns from A. Right, and then we just take the reducer echelon form and take the non-zero rows of the echelon form, and so this is what's going to be called R, sort of CR, right? And so we get this A equals CR. This is a decomposition of the matrix A into columns of A plus rows of the reduced row echelon form. And you can actually read off just lots of information about your matrix from this representation. Like it tells you all sorts of nice stuff about dimensions and things. I mean, things we're not going to talk about here, but it's a nice application of using what is really a very calculation-based process to prove theorems in some sense. You use this Gaussian elimination to get this decomposition, and then use that decomposition to prove things about matrices. So it's just an interesting, interesting aspect. Part of the point being is that Gaussian elimination is used for a lot more than just solving equations. I mean, one thing it's used for that I mentioned directly is finding representations of the null space. Here, right? So that goes beyond already just solving systems, because basically if we had all the language around, we'd be saying we're finding a basis for a null space of A. Okay. But it also gives us this nice decomposition, and it gives us more. It gives us LU decompositions and all sorts of other things. Anyway, I am going to stop this video here.